So let's make sense of this Euclidean algorithm a little bit. Anyway, if you let A equal A prime D, then D stands for a divisor of A. And B be B prime D. So D is the common divisor of A and B. 1 is always a common divisor, right? So A could be A times 1, B could be B times 1, and 1 is the only common divisor. But, I mean, we don't, so that's like the trivial one. So we know that A minus B is A prime D minus B prime D, which is A prime minus B prime D, as this is a common factor, the distributive property. So A minus B is, now A prime and B prime are considered to be integers, natural numbers. So when you subtract, you get some integer here that it's an integer multiple of D. So D is a divisor of A minus B. So this, in fact, so A equals so anyway, let's do a problem. And I'll show you the, oops, I dropped my thing here. Let me show you an example. So the general way this works is, if A is greater than B, you write essentially A equals BQ plus R. So if A is a bigger number than B, then you can do some multiple of B to get close to A, and then you add the remainder to that, and then that would be A. And you know the remainder is smaller than B, because, I mean, if it was bigger than B, then you could write it as B plus a number, and that could be moved over here, and then Q would just be a little bit bigger. So in other words, the remainder is always going to get smaller. That should make sense. So it turns out the Euclidean algorithm is repetitions of this, where you start with like Q1 and R1, and then you do B. Anything that divides A and B, you subtract these, it's going to be a divisor of R1 based on that subtraction we did. So in other words, B will be R1 Q2 plus R2. So a common divisor of A and B will be a divisor of R1. So the divisor of B and R1 will be a divisor of R2, but R2 is now smaller, because R2 is smaller than R1, and R1 is smaller than B. So they're always getting smaller as you're going down. So this process will eventually end. Now we'll make even better sense of this by looking at a particular example. So let's take the numbers 15 and 42. Okay, so 42 can be written as 15 times, let's see, 2 is 30. 3 would be 45. It'd be too big. So let's do 15 times 2, 30, plus 12. 30 plus 12 is 42. Okay. So anything that divides 42 and 15, the common divisor is going to divide 12. So let's take 15 now and write it as 12 times a number. 12 times 1 is 12, plus 3 is 15. And again, if this number was bigger than 15, then you can write it as 15 plus a number. And then you'd put it over here and it'll be like 3 times 15, or, you know, more multiples of 15. So this is always smaller than this. Okay, so now a divisor of 15 and a divisor of 12 is going to be a divisor of 3, but this is 3 times 4. The remainder is 0. So this number here is the greatest common divisor. It's the GCD. Oops, sorry. 3 is the GCD. So we can reverse these steps to get a linear combination, the common divisor, which is one of the ways this is used. So we see it terminated, and we know it's going to terminate because the numbers keep on going down. Now, 3 is 15 minus 12 times 1. Subtract 12 times 1 from 15, and that's 3. So 3 is 15 minus 12 times 1. So 3 is 15 minus 12 times 1. Now we want the common divisor of 15 and 42, but I have 15 and 12 and 1 here. But you see 12 is 42 minus 15 times 2. So this 3 is 15 minus 42 minus 15 times 2 times 1. You just keep on going back up, solving for the stuff to get up to the common factor, a linear combination, the greatest common divisor as a linear combination of these. So working back here, let's distribute the minus. So 3 is 15 minus 42 plus, multiply this by 1 and then distribute the minus, plus 15 times 2. Sorry, if I had a board or big board, I could lay it out in order for you. I'm just using this little thing here. So 15 and 15 times 2. So 3 is 15 plus 15 times 2. That's 15 times 3 minus 42. That's plus 42 times negative 1. So 45 minus 42 gives you 3. And here it is. 3 is a linear combination of the two numbers. Working back up, substituting. You know it's going to work at the end because the very last remainder is going to be one of the numbers minus a multiple of the other. So that's going to always let you, whatever this remainder is, it's going to be in the next step. And so you'll get a linear combination. I hope that makes sense. And so that's the division algorithm. It's basically writing A as BQ plus R. They do it over and over again. The remainders go down. You get a common divisor. What divides these two will divide the remainder. And then you can get a linear combination, the common divisor, as a linear combination of A and B by working your way back up. All right, thank you for listening.